Hello guys. Today we will be seeing this very important and interesting problem, binary search tree iterator. So basically the problem statement is that you have to design an iterator which will return the next value whenever you call the next function. Next is a function, and also there is also a function which has next, which is basically for checking if the next element of the BST is present or not. So for every next call you have to return in an in order style the node in an in order style, like the in order of this tree will be 3, then 7, then 9, then 15, and then 20. So basically you have to return 3 on the first next call, then 7 on the next call, and then 9 and 15 and so on. And has next is basically to check if like you are on the 3, and like if has next function is called, then in that case you have to return true if there are elements to the right of you, and if there are no elements like 20, so here you will be returning false. So this is the problem statement. So let's get into the question. Okay guys, so I think we should draw the tree first. So 7, 3, 15, 9 and 20. So basically if you see this problem, and what is the most fundamental approach which comes to your mind? Method number 1. Okay, sorry. So the method number 1 is where you must be thinking like to store this one in an array, to store the whole array. To do an in order, first is to do in order of the tree of the BST. Second, to store in an array, because arrays are very easy to manipulate, and here we basically want our recursion, like if we do a recursion on our let's say tree, so every time we do a recursion we have to stop at that point. If first next call is there, then the recursion must stop at 3, and then in the next call it should be at 7. So basically doing that in recursion is difficult. So you might think to store it in an array and keep a index variable, and depending upon the variable you will just increment the index variable, and based on that you will return the next value and the has next value. Similarly, fourth one will be you will just check from the array, check array, and return the value. So this one is very simple approach. This is a very simple approach, and this approach will take linear time, big of n time, because we will be traversing our tree only once and storing it in an array. So storing it in an array will take big of n space as well. So this is what we get from this method. So can we optimize this? Yeah, we can optimize this. So let's see a more optimized method number 2, where we will be doing some kind of solution, or you can say some kind of we will just like we will do a recursion, but we won't do an actual recursion. We will be just simulating our recursion, that we are doing a recursion, that is we will use stack. So it will be an iterative approach. Fundamentally it will be an iterative approach. So what we will be doing, let's see it. So like we draw the tree again. This is 2, this is 5, this is 10. I'm taking a different tree. 8, 12. So let me change the color. Okay, so what we will be doing in this approach is we will be using a stack. So how will we how our workflow will be going is okay, so since for a stack, if we go from the root to the left, then again to the left, so this is the way how we do an in order traversal, right? We will be storing the left things in the stack. We will be storing these things, like we will be storing 6, then we have 4, then we have 2 into our stack, and this is how our function will be starting off. So we will have a function in order left, and this function will take the root or any value which is coming from the from the stack or what. But since this will be called only once, because all the left will be stored in a stack, all the values of the left part will be stored in a stack. And what we gonna do is we gonna just pop a element from the stack, like we will be popping 2 from the stack, and check if this node has a right child or not, has a right child or not. Okay, so if this tree has if this node has a right child, then we will be just doing like what we did for the in order left. So we will be calling this function with the right child of node number 2. Okay, so in that case we will be just keeping all our elements in the stack again. So our stack will become like 6, then 4, then again 5 will be here, and since 2 is popped, and at this next call, in the first next call, we will be returning this value 2, whatever we have popped from the stack pop or stack top will be our next call return. Okay, and in the has next function, it's very simple. In the has next function, we will just check if the stack is empty or not. Stack is empty or not. Okay, so this is the fundamental approach. Let me just go over again. So what we are doing is we are using a stack. Okay, in the stack, the very first time what we do is we will traverse our tree, and we will store all the left part in a stack. So basically what we are doing is we will just call while root, and we will be storing in the stack dot append or push, whatever you use, append, and here we will be storing the root, and then we will just go to roots left. Okay, this is what we are doing for storing the left part in our stack. So this is our basically the in order left function. So this is how we store it, and then after that, if the next function is called, if we say the next function is called now, so in that case we will just pop element from the stack, check if it has a right child or not. If it has a right child, we will call the in order left function for the right child of that node. Okay, let's say if it's 4, in that case we will just check if it has a right child or not. So since we know that 4 is having a right child, 5. So we will call the in order left for the 5, and we will store since in order left will store the things in the stack for you. So there you will have the invariants, if you do a recursion, this is how the stack will be filled in recursion as well. So this is basically we are just simulating our recursion, but we are not doing recursion. Actually we are doing a type of recursion, but we are just trying to simulate how the recursion will be doing or playing the role. So that is how we'll do, and we will just return that popped value of the stack at each function call, and as at has next we will just return if the stack is empty or not. So let's talk about the time complexity. Okay, so since the time is very easy for, like, time will be big of n because we are just traversing the tree, so big of n time. And for the space, this is quite interesting, so let's talk about it little. Since has next function has next, first of all let's talk about the time individual functions. So has next is taking big of 1 time, right? Next function, this is basically taking bigger of 1 time in average cases, but in the worst case it will take bigger of n time as well. But the aromatized complexity is basically big of 1 in the average cases, right? So we are basically, whatever the quotient condition is, that we are satisfying the quotient condition, that since we have to just call every function in a big of 1 at average time. So this is what we are fulfilling. And the space let's talk about the space also. Since we are taking bigger of h space, where h is the height of the tree of the BST. So space is very easy because since for a stack we are just taking attachment height of the nodes in the stack, so that is the worst space which we are taking. And for the time complexity, it is very easy to see, because since whatever you're seeing is that important thing in this is that the call for a node for the right child is simply that we are returning at every call in the next function, we are returning the popped element of the stack. The only case where if it has a right child, in that case, if the node has a right child, in that case we are actually calling our in order left function. So in that case we might be taking big of an n space, so that is the worst case. So this is what we have. So thank you guys, thanks for watching.